Hey everyone, and welcome to This Explainer. Today, we're going to completely change the way you look at uncertainty. We're stepping into the shoes of top-tier business strategists and uncovering a mathematical tool that essentially acts like a crystal ball. I'm talking about the binomial distribution. We are going to learn exactly how this concept serves as a step-by-step guide to predicting business success. But first, I want you to really think about a critical question. How do the world's most reliable companies actually predict success? Is it just, a gut instinct, or maybe exceptionally good luck? Well, I'll let you in on a little secret. It's neither. Behind closed doors, they rely on a very specific statistical tool to prevent major business catastrophes long before they ever happen. So here is our lesson plan for today. We're going to quickly cover 1, basic model concepts, 2, the rule of independence, 3, the step-by-step formula, 4, real business decisions, and finally, 5, a practical example on quality control. All right, jumping right in. Section 1, basic model concepts. We're going to start with the foundational building blocks of this model, and that starts with the Bernoulli process, named after Jacob Bernoulli, who studied this extensively way back in the 1600s. Now, just like the binary code of ones and zeros that runs the very computer or phone you're using right now, every single trial in this model boils down strictly to 2 possibilities: success, which we denote with the letter P, or failure, which we denote with Q. There is absolutely no gray area here. You either get a heads or a tails. A product either passes inspection or it fails. Okay, let's dive into this next crucial part. Section 2, the rule of independence. To keep things super simple, let's contrast 2 basic actions to show you what independent trials actually mean. On the left, we have flipping a coin. If you flip a coin and get heads, the chance of getting heads on the very next flip is still exactly 50%. The coin has no memory. That is an independent trial. But look at the right side. If you draw an ace from a standard deck of 52 cards and you don't put it back, well, the deck only has 51 cards left and only 3 aces. The probability has completely changed for your next draw. That's a dependent trial. For the binomial distribution to work, we absolutely must have independent trials, just like that coin flip. Moving right along to Section 3, the step-by-step formula. Now, take a deep breath. I know statistical equations can feel a bit intimidating, but we are going to treat this formula just like a simple baking recipe. Now, what's really interesting about this slide is we only need 4 straightforward ingredients. N is your total number of trials, or experiments. X is the specific number of successes you're looking for. P is your probability of success in a single trial, and Q is simply the probability of failure. And honestly, because there are only 2 outcomes, Q is always just 1 minus P. If you have the right ingredients, you'll get the perfect result every single time. Absolutely nothing to be overwhelmed by. So whenever you face a problem, you just follow these 4 simple steps. Step 1, clearly define what a success and a failure actually look like for your specific situation. Step 2, determine N, how many total trials you're running. Step 3, find P, your constant probability of success. And step 4, decide on X, the exact number of successes you want to calculate the probability for. Once you line these up, the math literally does all the heavy lifting for you. All right, Section 4, real business decisions. Let's step out of the classroom theory for a second and look at how this math is utilized by major industries every single day to protect their bottom line. You'll find the binomial distribution working behind the scenes in a ton of different fields. It's used in public opinion polling to predict elections, in medical research to test drug efficacy, and in insurance to evaluate risk. But today, we're going to focus specifically on that very first bullet point, the high-stakes world of manufacturing quality control. And this brilliantly illustrates our final segment, Section 5, practical example, quality control. I want you to imagine yourself as a quality control inspector on the floor of a really busy manufacturing factory. You need to pull a sample batch of 25 parts off the assembly line to check them. Based on historical data, you already know the probability of any single part being defective is 2%. So looking back at our recipe, N is 25, and P, our probability of a defect, is 0.02. By plugging those exact numbers into our binomial formula, we generate this visual risk profile. Notice how the highest probability by far is finding 0 defects, followed by a slightly lower chance of finding exactly 1, and an even lower chance of finding exactly 2. This right here brings the abstract math to life. You can literally see your risk profile mapped out right on the screen. Which brings us to a totally critical threshold here, the number 3. If you run the binomial math for finding 3 or more defective items in a tiny batch of just 25, the probability is incredibly small. So if our inspector actually finds 3 defective parts, the binomial distribution essentially sounds a massive mathematical alarm. It tells the inspector that something has fundamentally broken down in the manufacturing process, and they need to reject that entire batch immediately. So the crucial point is this. What looks like a dry, textbook statistical formula is actually the foundation of business reliability. Mathematical concepts like the binomial distribution are the invisible backbone of reliable manufacturing and business. They're exactly what allow companies to make confident, data-driven decisions rather than just, crossing their fingers and hoping for the best. Which brings us to the end of our explainer with one final, kind of provocative thought. If you can mathematically predict failure before it even happens, how will you design success in your next big decision? I really encourage you to take this newfound analytical superpower and apply it directly to your own professional life. Thank you so much for joining me today, and as always, keep learning.